Okay, so now there is a technical, what you do is you take what's called a universal Turing machine. Most programming languages are universal, and the key technical thing in algorithmic information theory, which took us 10 years to realize, from the 1960s to the 1970s it took to get this right, is you want this property to hold. You want the information content to be additive, or actually subadditive is the term. In other words, the size of the smallest program to calculate two objects x and y at the same time should be bounded by the size of the smallest program to calculate each one individually, with maybe a few extra bits thrown in. That doesn't matter. This is the idea of a subroutine, that you should be able to combine subroutines to get a program, and of course subroutines are fundamental for programming computers, right? This was not true in the 1960s version of algorithmic information theory, because if you took the most concise program for x and the most concise program for y and you concatenated them, you get a bigger bit string, but you don't know where to separate it. So if you combine two programs which are both the smallest possible, you concatenate these two bit strings, then you have to add, for example, a number saying where to cut the string in two, and that's about an order of logarithm number of bits in the size of the sum of the size of the individual programs. So this was true only with a error term that was logarithmic order, you see. And the trick is to get it to be a constant here, rather than order of the logarithm of this. And you not only get this to work, once you get this right, everything else falls into place, as often happens in mathematics. So for this to work, you have a different notion a little bit of what a program is, or how your standard computer reads the program. The program is in binary, it's zeros and ones, and the normal notion sort of what a computer is and how a program works is that the computer is given the whole program all at once. The whole bit string. It knows where the bit string ends. That's the wrong notion. That's the usual notion. With that notion you have 2 to the n possible n bit strings. The right notion is that your computer is reading one bit at a time as it feels the need, as it's executing the program. And it will just go as far as it wants to or needs to. And there is no special mark at the end of the program saying there aren't any more bits. Because if you added such a mark, you would really, if you had a special character, like a blank, for example, syntactically marking the end of a program, of a bit string that's a program, you would actually be using an alphabet of 3 symbols, not 2, and the symbol that marks the end of the program is wasted, because it's pretty obvious that if you have an alphabet of 3 symbols, to really make the most concise use of it, you really want to use each symbol on the average a third of the time. And the symbol that just indicates the end of the program is a symbol that's wasted because it's almost never used. So if you're really going to have a binary alphabet, just zeros and ones, then you can't have a... So the idea is, so in other words, a program has to be self-limiting. It has to indicate within itself how many bits it has. And this is not hard to do. What you can do is you can put a prefix at the beginning of the program indicating basically how to read in the rest of the program. So a universal machine can essentially use any scheme to make what comes afterwards self-delimiting. There are simple schemes, like a simple way to make a binary program self-delimiting is to double each bit and then put a pair of unequal bits at the end as an end marker. But then you've doubled the size of the program. Another way is to count how many bits are in the program and put in front that number in binary. So that's, but that number itself, you don't know where that ends and the program begins. So you have to make the header, which gives the size of the program, self-delimiting too. So you can do that by doubling each bit in it and then putting on a pair of unequal bits at the end. Or what you can do is count the number of bits in the number which says how many bits there are in the program, put that in front. So this is like Russian dolls. Okay, so there are many possible ways of doing it, and a universal machine, basically, that can simulate any other self-delimiting machine, will basically be capable of using any such scheme, all such schemes, because you have a prefix at the front that tells you what to do with the rest, which other machine of this kind to simulate. Okay, so that's the idea, basically, of these programs. And if you don't do this, you can't define the halting probability. You don't have a way of having a probability over programs of any possible size all at once. If you fix If you think only about programs of a fixed size, then it's obvious that you make each one of them the same probability. But if you want to have a probability measure of all possible programs of any size, this solves that problem for you. Okay? So one of the things you get is you get this inequality. I like to use H like Shannon does for the size of the smallest program to calculate a pair will be bounded like this.
And with this requirement of the limiting still you may have a universal Turing machine.
Yes, no problem. However, before, most n-bit programs, most n-bit sequences require an n-bit program. These are the incompressible ones. But now, most n-bit sequences will require more than n-bit programs. They'll require programs which are like n plus log of n, because they have to be self-limiting. They have to indicate within themselves their size. Actually, it's going to be n plus the size of the smallest program to calculate n. That's precisely what it is. Okay? Now so once you've done this, the key thing is now you've got probabilities. Because every time the universal machine asks for the next bit of a program, you just do an independent toss of a fair coin. So now you have this probability measure on all possible programs. In other words, you have rigorously the idea that I think Emile Borel said first, at least that I knew. He had this idea of saying if you have monkeys typing away, what is the probability that they will type a famous work of French literature? Eventually they will. Right? So here the monkeys are not typing French literature, they're typing a computer program in binary, bit by bit. Eventually they'll type every program. And if it's an n-bit program, its probability will be 1 over 2 to the n. And this will work summed over all possible sizes. The total probability will be less than or equal to 1. Why? Because no extension of a valid program is a valid program. So you don't have any more 2 to the n programs of size n. You have a smaller number. Okay, so this is the crucial thing. Now, so now the question is, if which computer you pick, you end up with a different definition of program size complexity. And the ones you use in this theory are the best programs, the ones that have the best computers, the ones that have the most concise programs. Now, it turns out, in a way, if you're too demanding, there are no best computers. There is no one computer or one programming language which really has the most concise possible programs for every possible output. Why? Because for any individual output you're interested in, say the works of Shakespeare or Don Quixote de la Mancha, right? There always is a sort of a special purpose computer that has that built into the hardware, and with a program just 1 bit long, if the first bit is a 1, then it outputs Cervantes' masterpiece, Don Quixote de la Mancha. If the first bit is a 0, then it continues to read the rest of the program and interpret it as, as a program in C or whatever your favorite programming language is. So this is now a particular universal Turing machine or a particular programming language which has built in something very complicated normally, but now for this machine it's very simple. So you can't have a computer which gives you the smallest possible programs. Which would be, if you could, that would be the one obviously you'd want to use to measure algorithmic program size complexity. But what you can do is you can have the following. So what you have is you have a universal computer. This is any possible computer, C. And this is the binary program that comes as input, and C of P is the output. Okay? And your universal machine has the property that for any individual special purpose computer, C, which may have the works of Cervantes built in a library in the hardware, in a read-only chip that's in the part of the hardware. The way it works is your universal computer can always simulate what this computer, this is Turing's original idea expressed in a slightly different way, your universal computer U will do the same calculation that the special purpose computer does when it's given the binary, self-delimiting binary program P, if you give the universal computer the program P concatenated bit by bit with a fixed prefix which just says how this computer works. You see? And this is a fixed self-delimiting prefix. So the programs for this computer will be a few bits bigger than the programs for this computer, a fixed number of bits bigger, which will be the number of bits it takes to describe the hardware of this special purpose computer C. Okay, so these are the computers you use in this theory. You can take any one of them. Of course, if you're a physicist, you'd say, well, if you think of the physical universe as a computation, which is computing its future state from its current state, then there is a most natural choice of a computer, which is that computation which is most natural in the physical universe you're in. But that comes from physics. As a pure mathematician, I can't pick between any of these, but it doesn't matter. Whichever one you pick, you'll get essentially the same complexity measure, because there's only going to be a finite number of bits of difference. Okay, so when you use a computer like this, you want to compare how two of these universal computers, which are maximally expressive, they'll give you a slightly different program size complexity, but the difference will be bounded. It's the bound is actually the maximum of the number of bits it takes to tell u how to simulate v, and the number of bits that it tells to take v how to simulate u. And then whatever the object you want to calculate, the minimum size program to get u to calculate it and the minimum size program to get v to calculate it will differ by at most this number of bits, because you can transfer the program from one to the other and vice versa. Okay, so this is now one interesting thing about this. So the idea is what these universal computers give you that are used to define this theory mathematically is essentially the most concise programs, as much as that's possible. And I just showed you what the best possible is. Now, if you look about the algorithmic probability,